Feature engineering for credit models. Feature engineering means creating new data features that improve the performance of credit models. This is important in banking because banks use credit models to decide if a customer is likely to default or repay a loan. In this lesson, you will learn to build features from real-world style banking datasets for use with credit risk models. You will see step-by-step examples from beginner to advanced, using pandas and numpy. By the end, you will know how to extract, aggregate, and transform raw banking data into model-ready features. Running the cell now. Before we start, let us import all necessary packages. Set the random seed to 42 for reproducibility. Import pandas so we can work with tabular banking data. Import numpy for numerical operations and random number generation. Import warnings so we can suppress unnecessary warning messages. Disable warnings to keep our outputs clean while learning. Set the random seed to 42 so results can be reproduced every time. Running the cell now. Core data concepts. In practice, banks store customer, account, and transaction data in different tables. Transactions record each time money moves, with amounts, types, and timestamps. Customers may have one or more accounts, which they use for transactions. Credit models often require joining these tables and aggregating data over time. Common mistakes include misaligning joins, counting transactions incorrectly, or leaking future data when creating features. Running the cell now. Let us first create a synthetic customers table. We will use this as the foundation for our feature engineering practice. Generate a list of 200 customer IDs. Create a data frame for customer details. Add customer_ID as a column in the data frame. Tag the first 150 as retail customers and the rest as business. Assign their region, the first 100 as metro, the next 100 as regional. Finish creating the customer's data frame. Print the dimensions to confirm the number of customers. Preview the first 3 customer records. Running the cell now. This output shows a data frame with 200 customers, each having 3 columns, customer_ID, segment, and region. Notice the shape confirms 200 rows and 3 columns, aligning with the creation of IDs from 1 to 202 customer segments, retail and business, distributed across 2 regions, metro and regional. This setup models typical customer data organization, foundational for later joining with accounts and transactions in credit modeling. Try changing the proportions of retail and business customers to see how it affects segment distributions. Now let us create synthetic accounts. Each customer will have one account for simplicity. Start creating the accounts data frame. Add 200 unique account IDs. Connect each account to one customer ID. Assign each account a type such as savings, check, or credit randomly. Set an account open date spaced 30 days apart, starting in 2015. Display the data frame shape to check for 200 accounts. Show the first 3 account records. Running the cell now. The output shows a data frame with 200 accounts, each linked to a customer ID and classified by account type, along with their open dates. Notice the 4 columns capture essential account information, setting up the structure needed for later joins with customer and transaction data. This aligns with the lesson's focus on how banks organize different datasets before combining them for credit modeling. What would happen if a customer could have more than one account? Try adding more accounts per customer for practice. Next, we simulate real banking transactions. Each transaction will link to a customer, include a random amount, and record when and how it happened. Set the number of transactions to create. Start building the transactions data frame. Give each transaction a unique ID number. Randomly assign each transaction to a customer. Sample realistic transaction amounts with a normal distribution. Randomly label each as debit or credit. Randomly choose how each transaction occurred: ATM, online, branch, POS. Create a sequence of timestamps, 1 hour apart. Display the shape to see the number of rows and columns. Show a snapshot of the first 3 transactions. Running the cell now. This output shows a synthetic transactions table with 1,000 rows and 6 columns, representing individual money movements linked to customers. Notice key columns like transaction_ID, customer_ID, amount, and transaction_type, which are essential for later joins and aggregations. The hourly timestamps in date enable time-based analysis, aligning with the lesson's focus on integrating and summarizing transaction data across customers and accounts. Practice, try making all amounts positive and observe how this changes your statistics. Beginner example 1, simple transaction counts. A common first step in feature engineering is to count the number of transactions per customer. This captures overall customer activity and is easy to create. Running the cell now. Let us engineer our first feature, number of transactions per customer. Group transaction data by customer_ID and count the number of transactions for each customer. Show the counts for the first 3 customers. Running the cell now. This output shows the number of transactions each customer made, with the first 3 customers having 9, 3, and 6 transactions respectively. Notice how the code grouped the data by customer_ID and counted transaction_IDs to summarize customer activity. This simple count feature helps capture overall engagement, forming the basis for more complex analyses. Practice, try sorting this table by txn_count to see who is most active. Beginner example 2, total amount spent. Sums of amounts per customer show overall value of their transactions. You can later break this down by debit and credit flows. Running the cell now. Now let us engineer the total amount transacted for each customer. Group by customer_ID and sum all transaction amounts for each customer. Display the totals for the first 3 customers. Running the cell now. This output shows the total amount spent by each customer, with the sums calculated by grouping transactions by customer_ID and adding up their amount S. Notice the total_amount column captures the overall transaction value per customer, which is key for understanding individual customer spending before breaking it down further by transaction types like debit or credit. Try renaming amount to transaction_value for better clarity and see how the output changes. Beginner example 3, average transaction value. Average size of customer transactions highlights their typical behavior. This helps distinguish between small frequent and large infrequent spend patterns. Running the cell now. Let us calculate the average transaction value per customer. Group by customer_ID and compute the mean amount for each customer. Show the output for the first 3 customers. Running the cell now. Here, we see the average transaction value calculated for each customer, with columns showing the customer ID and their corresponding average spend. Notice how the code groups transactions by customer and computes the mean amount, which reveals typical spending behavior per person. This step is key to identifying whether customers tend to make smaller, frequent purchases or larger, less frequent ones. Sort the result by average amount to see who typically makes larger transactions. Intermediate example 1, ratio of debit to credit transactions. Customers with high debit to credit ratios may have different risk profiles. This feature captures transaction type behaviors. Running the cell now. Let us break down transactions by type and compute the debit to credit ratio. Group by customer and count debit transactions. Group by customer and count credit transactions. Merge these 2 tables, filling missing values with 0. Calculate the ratio by dividing debit by credit, adding 1 to avoid division by 0. Preview the output for the first 3 customers. Running the cell now. The output shows the count of debit and credit transactions per customer along with their calculated debit to credit ratio. Notice how each customer's ratio reflects their transaction behavior. Values above 1 indicate more debits than credits, which can signal different risk profiles. This code section captures these behavioral patterns by creating a new feature for downstream analysis. Challenge: change the denominator to avoid 0 by using numpys where to flag possible divisions by 0. Intermediate example 2, max transaction value per channel. The largest transaction per channel can be a signal for credit risk or fraud. High-value transactions are often monitored by banks. Running the cell now. Now let us calculate a feature for the maximum transaction value by channel for each customer. Group by customer and channel, then find the maximum transaction amount. Reshape the table so that each channel shows up as a column. Running the cell now. This output shows the maximum transaction amount for each customer broken down by channel, highlighting key columns like ATM, branch, online, and POS. Notice how some customers have 0 values for certain channels, indicating no transactions there. This table helps identify the highest transaction per channel, which is crucial for spotting potentially risky or fraudulent activities. Try counting instead of summing to spot unusual activity in certain channels. Does one channel show much higher values? Intermediate example 3, days since last transaction. Recency of activity can be important in dynamic risk monitoring. Customers who have not transacted recently may have changed their behavior. Running the cell now. Let us engineer a recency feature based on the date of the last transaction. Group by customer and find the most recent transaction date. Subtract that date from a reference date to compute days since last transaction. Show the days since last transaction for the first 3 customers. Running the cell now. This output shows the most recent transaction date for each customer and calculates how many days have passed since then, relative to February 11, 2024. Notice the days_since_last_txn column quantifies recency, which helps identify customers who may have changed their behavior due to inactivity. This step is crucial for dynamic risk monitoring by highlighting customers with longer gaps since their last transaction. Experiment: try changing the reference date, e.g., to the 1st of March, 2024, and see how this affects results. Advanced example 1, rolling mean of amounts, 3-month window. Credit models can capture changing customer behavior by using rolling features. Here we compute the rolling mean of transaction amounts, grouped by customer. Running the cell now. Let us engineer a rolling window feature for transaction amounts. Convert transaction dates to date time to enable rolling windows. Sort the data frame by customer_ID and date for proper calculation. For each customer, compute the rolling mean amount over a 12-transaction window, about 3 months if 1 per week. View the rolling mean alongside the original amounts for the first few rows. Running the cell now. This output shows the rolling mean of transaction amounts for a single customer, calculated over a 12-transaction window, which smooths short-term fluctuations. Notice how the rolling_mean_AMTA column updates gradually, reflecting the trend in spending rather than individual transaction spikes. This demonstrates how rolling features help capture evolving customer behavior in credit models. Try tuning the window length to 24 or 6 to see how shorter vs long-term behaviors appear. Advanced example 2, transaction standard deviation, variability feature. Customers who show a sudden increase in transaction variability may be changing risk profile. Let us engineer standard deviation of transaction amounts per customer. Running the cell now. Let us calculate the variability in amounts per customer. Group by customer_ID and apply the standard deviation on transaction amount. Present the STDEV for the first 3 customers. Running the cell now. This output shows the standard deviation of transaction amounts for each customer, a key measure of variability in their spending behavior. Notice how each customer_ID has a corresponding amount_STDEV, quantifying fluctuations that can signal changes in their risk profile. This engineered feature allows us to capture customer transaction variability, which is crucial for advanced risk modeling. Bonus: try replacing missing values with the overall average standard deviation. Advanced Example 3, One-Hot Encoding for Channel. Models need categorical variables converted into numeric features. Here we one-hot encode the transaction channel for each customer. Running the cell now. Let us create numeric columns for each channel to make categorical data usable. Apply one-hot encoding to the channel column and keep customer_ID to aggregate on. Some dummy columns by customer to get the total number of times each channel was used. Show the output for the first 3 customers. Running the cell now. This output shows the one-hot encoded transaction channels aggregated by customer, where each column represents a channel and the value is the count of transactions for that channel. Notice how each customer has varying counts across channels like ATM, branch, online, and POS, turning categorical data into numeric features. This summary is crucial for models to analyze customer behavior based on transaction channels. Practice: try this approach for account_type in the accounts table as well. Error handling and debugging: handling missing values. It is common for transaction or account features to have missing data. Let us simulate missing total_amount for a few customers and fill these gaps. Running the cell now. Let us introduce some missing values and then impute them with the mean. Copy our original sum data frame. Set some total_amount entries to missing NaN for demonstration. Show the table before filling to highlight missing entries. Print the head to see missing values. Fill missing total_amount values with the mean of available values. Show the table after filling for comparison. Print the head again to confirm gaps are filled. Running the cell now. Before filling, you can see missing values, NaNs, in the total_amount column for several customers, which could disrupt analyses or models. After filling, these NaNs are replaced with the mean total amount, ensuring no gaps remain and maintaining the dataset's integrity. This demonstrates a simple yet effective strategy for handling missing transaction data before further processing. Try using the median instead of the mean as a different way to fill missing values. Best practices and common patterns. Always set seeds, for example, np.random.seed 42, for reproducibility. Check your feature distributions for outlier values and missing data. Avoid data leakage, never use future information to create present features. Break down complex features into smaller steps, like counting then aggregating. Test engineered features for meaningful variation, not just technical correctness. Running the cell now. Tiny end-to-end problem, predicting default risk features. Let us simulate a simple workflow, bring together features, merge with customer segments, and prepare for modeling. We will use a synthetic default flag as the target label. Running the cell now. Let us put together engineered features from earlier and prepare a full feature table for modeling. Merge transaction counts, total amounts, and amounts dev into one data frame with one row per customer. Chain in the customer segment and region columns. Merge customer segment and region information from the customers table. Add a simulated binary default flag with a 10% chance of default as our target. Show the merged feature table. Running the cell now. This output displays the first few rows of our combined feature data frame, showing transaction-based metrics like counts and amounts, one-hot encoded channel usage, customer segments, and the synthetic default flag. Notice how each row integrates multiple data sources into a wide format, ready for modeling default risk. This confirms that our data merging step successfully aligns features and labels by customer, establishing the foundation for predictive modeling. Practice: try changing the default probability to 20% and see what happens. Want to master banking data? Watch our Pandas feature engineering playlist on YouTube. Takeaways and next steps. Developing strong feature engineering skills is key for banking model success. Practice aggregating, encoding, and handling banking data regularly. Try exploring public credit datasets for more feature engineering practice. For more deep dives, look for feature engineering walkthroughs on our channel. Running the cell now.